back to you.
Is there any way on the second homework we can do a few problems?
Yes.
Okay.
No problem. Yeah, we can spend the day today with exam review
That'd be
until
great.
everyone's,
That'd be
until
awesome.
everyone's satisfied. And if we have time left, we'll go on to our lesson. So let me mention something else before we get started. We have our new shirt set. And this is the brand new pink one. We've never had pink before. We've also got orange, which is a brand new color for us, and we're restocked in blue. And then we still have some black and white left over for us. So let me tell you about the shirt real quickly. There are a few kind of secret messages here. And these things at the top are a code. Each of these represents something that you can learn along the way here. This is electric and magnetic fields. Altogether, this is what's called the pointing vector. That's the name of the person. It's P-O-Y-N, not P-O-I-N. And the pointing vector, nevertheless, has a job of pointing in the direction which the energy of an electromagnetic wave, the momentum of an electromagnetic wave is oriented, propagating. So this cross is something we'll meet a little bit further along here if you haven't seen it yet. It takes the portion of two vectors that are at right angles to each other. So this, in essence, says that the energy of an electromagnetic wave, the direction of travel, propagation of an electromagnetic wave, is at right angles to the electric and magnetic fields. And this pointing vector, we normally use the letter S to signify its variable. This, anyone know what that is? That's a hydrogen atom. That's right. It's also the symbol of Dr. Manhattan, if you like watching. So that's a hydrogen atom. It's H. K log omega. This is an expression for the entropy in statistical mechanics. Entropy describes, if you like, the disorder of a system, or somewhat more literally, how many ways a system can be equally configured. So, for example, if you have all white socks, there's lots of ways to order the socks. If you've got one red pair, one green pair, one blue pair, one black pair, and you've got a separate section for each of them, then there are fewer ways to arrange it. That's not very good to say. Anyway, it's how many different ways there are to arrange a system. That's entropy, and the symbol for that is also usually S. This is force times distance integrated. We'll learn that as we come up. Force times distance, you've heard that before, probably. What's that? Yeah, work. If you take the negative of the work, that's the amount of potential energy that you store in the systems. This term represents potential energy. There are several different symbols that are used for potential energy, but sometimes used as the letter U. SHS. Exactly. SHS. And on top of that, these four symbols also represent the four main branches of our field that all undergraduate students meet in four separate classes, and then you meet them again in graduate school if you follow that track. So electrodynamics, statistical mechanics and thermodynamics, classical mechanics, we've done a little bit of that, and quantum mechanics. On the back here, we've got our university mascot. That's Sammy. That's Sammy the Schrodinger's bear cat. And he's in a little box there, and he's in a superposition of up and down states. So we would like to pass one of these t-shirts to each of you. So let me pass a sign up sheet around. And if you would please put your name and your preferred color and size, we'll bring those to you. They're Friday.
What kind of blue is it?
It's royal blue.
Or a little dark?
A little darker than that. Not as dark as Chad's shirt. It's not a navy. It's a royal. There you go. That's not good. The orange is sharp too. It's pretty bright orange. Those are our new selections. Okay. Any questions on the most recent homework section?
I guess the first one.
Okay. Would you read it for me so I can?
Okay. It says, a boy stands on top of a tall apartment building with a slingshot. At a maximum stretch, this device will fire a marble with a speed of 25 miles per second. He takes a shot aimed upward at a 30-degree angle and toward a second tall building located at 85 meters distant. How long does the marble take to reach the building?
Okay. And then the next question after that is a follow-up.
How far below the launching height will his marble strike the second building?
Okay, very good. So what we've got in this case is an initial speed that's been provided to us. A launching angle that's been provided to us. And we can use that to break up into our x and y components. No reason to do anything here other than just a straight coordinate system. So we have v naught cos and v naught sine for the x and y components of initial velocity. So as it travels, this thing will take a arcing parabolic path toward the building, and we are given in this problem the distance x. So distance x was 85. Meters. Angle was
30.
30, and initial velocity was 25 meters per second. Very good. So, let's set up our grid of known and unknown quantities for the x direction and for the y direction. So in the x direction, what do we know? Yep. So we know V initial is 25 cos 30. What else do we know? Dx is 85. Anything else we know in the x?
Acceleration be zero.
Yeah. So there's nothing to speed up or slow down along the x-axis. So acceleration is zero. That, yeah, you bet. So the final x is just the initial x. You can say we know that. The only thing we don't know is what? So the x direction in this case is the simpler motion, and we can use that to get our time. Once we have our time, we'll bring it over here and use it for the y motion as well. What else do we start off with knowing in the y direction?
Acceleration.
Good. So we've got negative g. We'll use 9.8. And we've got what else? Yeah, exactly. So you know what y is 25 sine 30. And we don't know what? We don't know the final velocity or distance traveled in the y. So that should be obvious now that if we don't know t yet, we don't have enough information to do the y, but we can get the t from the x. Let's get our kinematic equations up. So d is v naught. We'll say t. d is v naught t. T squared over 2. Average velocity times time. So to solve for t, which one would you like to use?
Our first one.
Will that work? No. So in these zero acceleration cases, in some sense you could say this equation doesn't really have a t in it because it's multiplied by zero, so that's no good. What could we use? Will the third one work?
No, because it's not.
That's also indeterminate in this
What if we
case.
use the last one?
Yeah. Last one will work just fine, or the second one would also work just fine. In fact, without that acceleration term, and with the initial and final velocity being the same as each other, don't those equations say exactly the same thing?
Sure.
They just both say distance is velocity times time. Which is the right thing for no acceleration. So dx is v naught x times time. Time is distance over velocity. So we've got 85 over 25 plus 30. You have a number for us?
For time.
3.93 seconds.
Can you agree with that?
I got 2.9 for it. Maybe I did it wrong.
Okay, I'll guess the difference is between those two answers, whether we're actually dividing by the constant. So remember, everything that's in the denominator gets its own divided by. So let's make sure we enter this as 85 divided by 25 divided by cos 30.
Okay, yeah.
So 3.9?
Mhm.
3.93 was it?
Yeah.
And units per second. Now, just to comment on that, again, real briefly, there's two ways to do that. You could do it as 85 divided by parentheses, 25 cos 30. And then parentheses groups the things so that you're dividing by the whole bit.
And that's what I did.
That'll work just fine. If I were entering this in my calculator, I think the simplest and most straightforward thing to do is just everybody on the bottom gets a divided. Okay, we've got our time now. The next question actually asks for distance traveled in the y. So I think maybe the most straightforward thing is just to use v naught y t minus gt squared over 2. So if we put in our numbers, we've got 25 cos 30.
What did we sign the 30?
Oh. Yeah. Something like that. 35 sine 30 times 3.93 minus 9.8, 3.93 squared over 2. Let's get a number on that.
1?
Give me a second now. Let's see, this is about 4. 4 squared is 16, divided by 2 is 8, times 10 is minus 80. Sine 30 is a half. So that's 12 times 4 is about 48 minus 80. So I guess the answer should be in the ballpark of negative 30.
Negative 26.5. I'm not sure.
This sounds rightish. Let's put that in our calculators again, make sure we don't get the right answer. Good.
Yeah. So it'd be more like if you wanted to be technical, it'd be like negative 26.56, if you want 2 decimals, or
It's all business. Everybody getting the same answer on your calculators? Everybody double check something? Okay, good. Let's go ahead and do one other thing here. I don't think this was asked by the question, but it's very likely you have a question of this type, and there are other questions of the type on the same homework set. So let's ask ourselves also, what's the final speed and the angle of traffic? So in other words, in what direction was the ball or marble headed right before it struck the far side? So, what we want to do is to consider this triangle. Very important, this triangle is made out of velocities. Final velocity x, final velocity y. So final velocity x is just the initial velocity x. It was 25 cos 30. 28-ish. Oh, this was on 20-ish. 25 cos 30, what is it?
is it 25 plus 30?
25 cos 30.
Okay, plus 30, 21 plus 6.
And then for the y direction, we can get that, for example, just using our first equation there. So d naught y plus at, where a is negative g. D naught y was 25 sine 30 minus that way 3.93, so that's about negative 40. That's plus 12 and a half, so negative 27.
Negative 26.
26.01.
Oh, 1.
Again, when I write that on the triangle, I'm going to use an absolute value sign there to indicate that it's just a magnitude, a length of the side of the triangle. And once we know the two sides of the triangle, and that it's a right triangle, we know everything that it's possible to know about the triangle. The total speed is the hypotenuse. So for the total final speed, we're going to do square root 21.6 squared plus 36 squared.
33.8.
Okay, that sounds right. Velocity, meters per second. And what trig function would be most handy for getting our angle?
It would be the,
Yeah, exactly. Let's use the tangent and then take the inverse tangent. So let's say tan theta is opposite, just the 26, over the side close to the angle. We've marked the angle we're referring to. So 21.6.
that'd be about 50.3.
Okay, good. That sounds right. Tan inverse 26 over 21.6. Okay, you want to second that? It seems right. Long size there, so it's going to be a little more than 45 degrees. Now, real quickly, let me point out the most common wrong answer to that particular question. Just don't write this down. Just point it out so that you can. The most common wrong answer is to look at dx and dy and to look at that angle. So that angle would be an inverse tangent of distances. One can calculate that angle, and it is the right answer to a certain question, but it's not the question that's been asked, so that's the distinction. Make sure you're clear about it. This would be the right answer to the question if I were standing on top of the roof and I noticed that I had just broken a window. How far down would I have to look to see the window on a straight line? So that would be a question that was related to distances. In fact, what we wanted was the answer to the question, in which direction is the ball moving? So moving has to be related to motion and velocity. So if we want to figure out which direction it's moving, we need to compare its motion in the y to its motion in the x.
So basically, how far back do I need to go so I don't get seen?
Okay, good. Everyone happy with that question? Does that win in and out? Excellent. Any other questions from that homework?
Yeah.
Hmm?
Okay, are you ready?
Sure.
Okay. It says a cannon is fired with an upward vertical velocity of 30 meters per second and a sideward horizontal velocity of 50 meters per second. How many meters from the launch point does the prior cannon ball land? And use G equals 10.
Perfect. So that notion there, G equals 10, that's intended to indicate to you that this is maybe a problem you can do in your head. That's what we're talking about. So let me walk you through that. It's a very nice problem. I like it quite a bit. Partly because you can do it in your head. That's what's kind of fun. It's also a very practical problem in some sense. We're an artillery person from Penfield, or maybe you're a hunter in a football game, something slightly less violent. And the scenario is just that our landing height is the same as our launching height. I guess that's broken slightly because of the cannon being elevated, but let's assume maybe there's a slight hill at the place where the thing lands to take out the difference. So we're going to have a total initial velocity. We've got that broken into the x parts and the y parts. In fact, in this one, in this problem, rather than giving a total velocity of an angle, you're just given the x and the y parts right off the bat, right? So the x was 30,
Yes.
and the y was 50. Perfect.
It's actually the other way.
The other way
Yeah,
around?
yeah, sorry.
Okay, so 30 meters per second vertical. and 15 meters per second horizontal. And ultimately, what we want to solve for is the horizontal range, right, of vertical travels. Now, I'm going to suggest to you again that if you think about this problem in the right way, kind of like the well problem, we dropped the rock down the well. If you think about this problem in the right way, it's actually one that you can do very simply in your hands. So I want to give you that challenge and let you mull it over for a few seconds here and see if you can figure out what a strategy to attack this. You certainly can do it using the kinematic equations and doing X and Y tables, all of that systematic approach will work just fine. Let's see if you can find a shortcut.
We're trying to find which one, view?
Given VO, we want to find how far away the thing lands, the distance, the range. What's that? You're warm. You're warm. That's not the right answer, but it's related to the right answer.
Do we find our time?
Time is a good thing to find. Which of these motions would be simpler to use to find the time? The vertical is right. See if you can figure out a shortcut to quickly figure out what the time is. And I think you're warm. How'd you get 5?
I got 3 from G and 30 because B up in the air for 30 meters per second. I think that all 10 meters per second as well.
I think we're a little confused there.
So the velocity is 30, and then it's 20 the next second. And then
But, yeah, we don't. Okay, good. I may have spoken too quickly on what you said there, so we'll come back to that if I misunderstood. Okay, go ahead.
After that first second, I'm not sure if it's 15 or 10.
Okay, so what do we know about gravity? We know that gravity steals your vertical speed at 10 meters per second per second. Or do you want to say again what you were saying? Or okay, go ahead. Okay, go ahead. Let's follow this thread. So the initial vertical velocity is 30. Okay. So after 1 second, the vertical velocity will be 20. Then, after 1 more second, from 20 to 10. Good. And then after 1 more second, from 10 to 0. Okay. So when your vertical velocity hits 0, what position are you at? You're at the top. You've gone as high as you're going to go, and you're just about to start moving down again. So I would suggest that the shortcut to this problem actually involves breaking it in half. Now, that's usually not a good thing to do, actually. The only time that you want to break it in half is if the two sides are in balance with each other. And in this particular case, since the takeoff height and landing height are the same, the two sides are in balance, we can actually simplify things a little bit by breaking the problem in half. So we can ask ourselves a question like this. We know that at this point, we've got Vy equals 0. So the question is, how long did it take to get from here to there? 3 seconds. So we started off with 30 meters per second of speed, and gravity is going to come steal those away from us at a rate of 10 meters per second of speed per second. So it'll take 3 seconds to get to the top. If it takes 3 seconds to get to the top, all the way back down takes another 3 seconds. This system is symmetric, it's balanced. So total time would be 6. So distance traveled in the horizontal If we're traveling sideways at 50 meters every second, and we do that for 6 seconds,
300.
300. Make sense? You were missing the half. Yeah. So I think you might have been on the right track there. We were missing the half. Let's do another one, closely related, but let's mix it up a little bit. See if we can get the answer. What if we did this? Okay, so let's flip it. Instead of 50 and 30, let's do 30 and 50. New problem. Run through that one in your heads and see which one. Just look for the distance. And what you got 300? You got 300? Did anyone else get anything? 300? You sure you're not doing the other problem? You did the new problem. Let's check. Okay. So how long are we going to spend in the air?
10 seconds.
10 seconds. 5 to get up, because we have to take 50 units, and we're there taking 10 at a time. Continuously, but each second a total of 10. So 5 to get up, 5 to get down, 10 seconds total, moving sideways at 300 meters per second, sorry, at 30 meters per second for 10 seconds. How far do we go? 300. Huh. Does anyone have any questions about that result? So it turned out to be the same number, right? What's the next natural question to ask? In particular, in response to the fact that the number came out the same, what would be a natural question to us?
Can we use this with any problem like this?
So the question basically would be, was that a, yeah, what,
But they, I'm not got two rows from some all problems like that.
okay, was it a coincidence? You think it always turns out that way? If you switch the x and the y, it comes out the same?
No.
So you think it was a coincidence? Just the numbers that we were using? I think I'm misunderstanding.
It wasn't.
Not a coincidence. How can we check if it was a coincidence or not?
Put in different numbers.
Okay, we could do it with different numbers. Now, if we did it with different numbers and they gave us different answers, well, then we would know for sure that it was a coincidence. If they gave us the same numbers, would we know that it was not a coincidence? Would we?
I would say you'd have to test it more than,
How many times do you think we'd have to test it to know for sure? All of them is the right answer. Do you have that much time? You do have that much time. It's real easy. How do you test all of them at once? A formula. That's right. So the note is very important. This is sometimes why we don't like to put our numbers in until we get to the end. Because if we don't put our numbers in until we get to the end, then we have a formula, and we can tell for sure the way all the cases behave all at once. Not putting the numbers in is the best way to do everything at once. So let's try that. Let's say this. So time, let's do time up. Okay? So time up is going to be whatever the initial velocity in the y was divided by g. By that. So isn't that what we did? If you like, that's just this equation with v final equals 0 and a equals negative g. So if that's 0, what is t? Let's bring this over here. It's minus AT, but A is negative G. It's GT, so T is V naught over G. In other words, gravity is stealing. Gravity is stealing our initial y velocity at 10 units per second. So, time total is twice time up here. And distance traveled in the x is v naught x times time, right? So, if we put all that together, it looks like dx is 2 v naught x v naught y. If we switch the x and the y initial velocities, does it always come out the same? Yeah. So it wasn't a coincidence. This was built. In fact, if we had written this in terms of the angles, we would have a slightly different formula, right? If we had written this in terms of the angles, v naught x and v naught y, they would be, x would have been adjacent to our launching angles, so that would be v naught cos and v naught sine. So this would be 2 v naught total squared cos theta sine theta. Let me ask you another interesting question, which is maybe related. What's the best angle? Why did you say 45? Right in the center? Feels right?
This angle for what?
That's an even better question. My question was kind of, yeah. So that's the first thing I wanted to know. The question was bad. So both of these answers are perfect. So if I want to say best, I gotta say best for what? Now, what did you assume I probably meant? Best for, well, you have to say what you're trying to maximize, right? Best for maybe longest distance travel. That would be a pretty natural thing to maximize. Before we get too far along in the semester, we're going to learn how to maximize these things explicitly. But this question, because of the certain symmetries in it, has an answer that can be guessed. And sure enough, the answer is 45 degrees for maximum distance. So what's the reason for that? Yeah. If you go too high, you're just not spending much of your velocity in the forward direction. You don't travel very far. On the other hand, if you go too low, most of your velocity is forward, but you don't spend much time in the air. And since we know that if you kick the ball straight up, how far does it go? Nowhere. And if you kick the ball straight sideways, it never left the ground, so how far did it go? Nowhere. And sure enough, those are the same as each other, 0 and 90, switching x and y. And then we know that these will give the same answer. These will give the same answer. These will give the same answer. These same as each other. Oh, and then 45 is the same as itself. And then we just have reversed, right? So it must be that transition between going nowhere and going the maximum distance.
Does that change with if you hit like escape velocity?
Okay, this is an even better question. So if we've got wind resistance, which certainly would apply, for example, in a football game, then the answers can be modified a little bit. And it's not something that we can calculate as easily, maybe not at all, with the formula, but we can do it in a computer program, for example. To continue the football question, and to continue the question of what best means, do punters in football games kick at 45 degrees? Generally not. What do? A little shallower or a little steeper? Well, sometimes. Depends on what their goal is, actually. That's a good answer. Sometimes they'll go a little steeper in order to optimize what? Additional, what do they call it? Hang time. Because if you optimize for distance, you might outkick your coverage. And then the return specialist has a full head of steam before your coverage gets outfield. If you go a little steeper, get a little extra hang time at the price of a little distance, but more likely to force a fair catch, for example.
I have a question
Yeah.
about number 11. It's related to the cannonball. It's what is the maximum height of the ball?
Perfect. Well, in this particular case, we can also do that in our heads. Our initial velocity in the y was 30. Our final velocity in the y was, well, not final.
Negative 30.
Yeah, final is negative 30. But if we take this to be, so 0. So the average velocity on the way up was what?
15.
15? And how long did it take us to get to the top? 3 seconds. Average velocity 15, 3 seconds, 45 meters. And of course, that can also be done with the kinematic operations. Okay, so let me mention any other questions from that homework set? Okay. So let me mention a few other things to be on the lookout for on the exam that's coming up. In a nutshell, this section that we've spent the first part of our semester on has been about our basic functions, mathematical functions, and solving for x. So what types of functions have we seen? Well, we've seen powers. We've seen exponentials and logs, powers, let's say. Polynomials. Exponentials and logs, and then the trig functions most recently. So, the first thing that you should make sure you're adept at are the drills that have been done in the recitation section with Caleb. You know, the drills in the recitation have been a little bit more repetitive, a little more traditional mathy type problems, right? So any of those drills, you're very likely to see one from each basic category of the drills that you've done with Caleb. Make sure you have good mastery of those reducing functions that have logs and exponentials in them. For exponential and log type problems, we did a few together in this side of the class. One that we did, for example, was the terminal velocity problem, or at least we looked at it a little bit conceptually. Or the radioactive decay is the same thing. Discharging a capacitor is the same thing. So if we look at radioactive decay, for example, we knew that this thing was going down like that. Right? So this is the number of things. It starts off at some time 0. And the number of things is whatever you had at time 0 times e minus t over the time constant. So, for example, I could give you a time constant, and I could say, how long does it take for 95% of the radioactive material to decay? So if I asked you for 95% to decay, I would want n over what you started with to do what? How many you've got relative to what you started with. If 95% are gone, how much is left? 0.05. So 0.05 is e minus t over tau. Then take a log of both sides. Log 0.05 is minus t over tau. So t is minus tau. Well, if I gave you a time constant, you could turn that into a time. So that might be one sort of thing in the exponentials and logs. We did the log-log plots. Most of you did great on the plotting of the planets. I think a few of you may have misunderstood the instructions on the musical scale. I wanted you to do it on a spreadsheet for all cases between 1 or 2 and 24. A few of you just did 24. I think one of you did all 24 cases on a spreadsheet. the log plotting that could be there, that could be relevant. Obviously, a few of the kinematic questions. So those are basically, can we set up a word problem? Can we solve the algebraic expression? I think we did some word problems in the recitation that were like, somebody has some nickels and some dimes and some quarter or something like that. How much of each do they end up having? And some other constraints.
So any specific equations that we will have to have in our head?
I will provide you with the kinematic equations. You should certainly know the trig functions in regards to what they mean and how to use them. I'll give you the kinematic equations. If I give you a problem like that, I'll provide you with that. There'll probably be some application problem for trig. We could do the statics problem that we did the other day when we had the guests in class. What's the tension in each of the chords? That's a very nice algebra plus trigonometry type question. We could do the problem, if you like, from the recitation where we have, let's see, we did one in class that was like the height of the Washington Monument, let's say, or something like that, or there could be a building with an antenna on top, and you have a couple of different angles. So some applied trig problems like that, and then also probably just some basic, here's a triangle, use the correct relationship to
Figure out.
to tell me a side based on okay, everybody set? Test will be on Thursday, tomorrow, normal lab time with Caleb. And then I'll see you back in class on Friday and we'll do that bicycle problem. You're welcome.
Could you talk to me a little bit about the stream problem we were just talking about?
Yeah.
I don't know.
Oh, okay. So, that problem was set up as follows. You can imagine it to be a tightrope walker or some mass suspended from a voltage. We have an angle 1 and an angle 2 and some weight in G of the object. And we have our tensions pulling as such, and we want the we want the system to be in balance. Oh, just right there. So to put this system in balance, we need our x forces to add up to 0. So that's the one. That's so T1 cos theta 1 negative plus T2 cos theta 2. That's our forces in the x. Basically, no acceleration. The system to be in equilibrium. And then the vertical plus T1 sine theta 1 opposite side plus T2 sine theta 2. Those go up. Gravity's pulling down. We want that to balance the system.
Ian's going to take this to lots of power.
Perfect. Then we have the system of two equations.
So how do we go on this? We just, any numbers that we would be given? Tensions?
No, you'd be given the angles and you guys solve the equations. So, you could solve this with our T1. I'm just crossing it out. I'm saying there's no acceleration. So if the system's not accelerating, the forces have to add up to 0. This is not per room volume, it's just for the video. Like a laser pointer slide advancer?
Oh, I've got
You
it.
got it.
Thank you. Would you like me to wear this? Or
Yes,
is-
if you would, please. So that can go in pocket or whatever you like, and then.
Where are the cookies? Not that I need that.
I saw him walking briskly away from here, so I don't know if that's what that was about. I thought U of H was like at least a month ago if you're trying to get funding. I thought it was for 2 weeks. I'm assuming you're math. Oh, yeah, yeah, yeah.
So who are these people here?
Hmm?
Yeah.
They wanted to come. They're not forced or anything.
Oh, so this
Oh,
one.
there's my lab.
Okay. So any geology people here? Geology? Who's a math major? Oh, that's good. So these math majors, so is this, which class is
Physics 2.
1422 or,
Mm-hmm.
so are you seniors or?
I yeah, no, weird, yeah.
Oh.
Do we look old?
Yeah, you look really old. Yeah. So are you guys thinking of going to graduate school in math?
Yes.
And University of Houston, is that what you're going?
That was just my thought.
I think there's a master's in mathematics here.
SMU?
Oh, here at
Oh, okay.
we have 3 minutes.
Can you tell, do you know some jokes or something?
Yeah, go ahead.
What if the window says I'm removal energy? I'm a big fan of it.
Okay, I have a joke. What's the unit of energy?
Oh, yeah?
No, what's the unit of power? I'm sorry, I don't even know the joke. Thank you. My joke was bad. What's the unit of power? Other jokes?
Think of some science-related ones that would get me in trouble.
Oh, I have one. It can't have to be clean like we do. Okay.
How many calories does the Texas rainbow make up? If he wrangled out of 99.
Oh, say that again? How many cows did he wrangle?
Yeah, if he wrangled out 99.
He wrangled up 99.
Actually wrangled out 100. Did you round up?
Oh, he's just like.
Oh.
Is he rounded them up?
Good joke. Yeah.
That was a good one. All right. Good afternoon. My name is Peter Flaming.
Oh, we know we have to officially introduce.
Okay.
Joel, do you want to officially introduce?
Please.
this week?
Please go ahead.
Do you have the official shirt? Or
Dude.
tell me if I'm doing it right. You know, I've had a lot of practice. You know. So we're very happy to have Peter. How do you say your last name? I can't remember.
Flaming.
Fleming, yeah. And Peter, I met him at Kroger in the Woodlands. No, seriously, he was a 1302 student at SAM, and he got his BS in geology. And he was in the military for several years, and then he went back, got his geology degree at SAM, and now he's doing data science at SMU, and we're very happy to have him here. And Dr. Walker has gotten these fantastic gifts, a shirt, official physics shirt,
Thank you.
and now, you know, because you're a data scientist, you need a very advanced computing device.
I'll put this next to my slide rule.
Yeah, that is it. Yes.
Thank you. And thank you for inviting me to come and do this. This is awesome. I love being able to share my joy of learning, and I also want to motivate everybody to stay curious, because even in the program that I'm in now, there's always those individuals that don't want to progress any further than they have to. They just want to get that A, and they want to data dump their brain when they're done. So stay curious, my friends. All right, so my name's Peter Flaming. I am a data science master's student at Southern Methodist University. I am on my 3rd semester. I'm on a 5-semester track. So this summer, we have 15-week semesters throughout the summer. So it's like continuous 15-week semesters, spring, summer, fall, spring, summer, fall. So this is my 3rd semester. I'm currently taking a data mining course and network security, so a lot of cryptology. And there's some really high-end math in there for all you math majors. You guys will really enjoy some of the cool ciphers that are being built. I'm interested in how machine learning can break them. So we don't really get to do too much of that, because they're there to teach us how not to do that. This talk was mostly motivated from my encounter with Dr. Friedman, and he was just interested in what I'm doing, and it's like very non-traditional. You know, I went from geology to data science. You don't hear that very much. In the Houston area, it's more popular for physicists, mathematicians, statisticians, and engineers of all sorts. At my school, there's like chemical engineers, civil engineers, structural engineers. They all love the static and dynamic, and they can apply it to the mathematics skills that they have. They can apply it to the data science. Being creative and thinking outside of the bubble is definitely key. And that's something keep in the back of your mind when you see this code and all the different topics that I'm going to go over. don't just see it as an example, see it as a way that maybe you could apply it to something you want to pursue or even the research you're doing now. And another thing I really love about data science is it's open source. So coming from geology, a lot of the geology stuff in oil and gas especially is not open source. Everything's secret. So the data that I have here, I had to acquire from going to workshops and actually being given the data. And you can't just go and download it from the internet. All the open source stuff that you can get from the internet for geology and well logs, it's garbage. So you can't build very good models. Trash in, trash out. So let's go ahead and begin. So here is the picture that I put on the flyer. I really like this picture because it summarizes with a nice Venn diagram of what data science is today. So data science has been around fairly recently for like the actual key word data science and like what it is modern today is like maybe since 2009. 2012, it came out as like the sexiest job in a Forbes article. But it's mostly statistics. As you can see, the multivariate and uni and bivariate statistics, those two areas of that validity section of the key like skills that you must have, that is what's important. Because if you can't be significantly sure on what you're producing with your models, what's the point of the model? So that's definitely something that's very important to data science. So as you can see, the hacking skills, can anybody take a wild guess on what you think that has to do with? Like we're not being like hacking the internet and breaking into your bank to try to get your information. How would you see a data scientist utilizing hacking skills? Anybody?
Manipulating software that's already in existence to fit your goal.
Exactly. So we take actual research that's being done in any field. So for example, Dr. Friedman and I were talking about image processing. You could take the same algorithms and models that they built and trained to utilize actual pixel by pixel learning, whether it's deep learning or even just logistic regression and like principal component analysis to do some other stuff. We'll talk about that later. You can take that model and apply it to your domain, which is why domain expertise is also a key part to data science. So traditional software, you hit it right on the head. We take all the programs that people are providing for a big price and selling to companies that are just allowing analysts to go in and click buttons and provide a spreadsheet or create a business intelligence actual dashboard to show their boss, and then everyone's happy. So data science is, we're kind of evolving past that now, where we're actually going in to all these different softwares and seeing how it's working, understanding the mathematics that was going behind the doors, underneath like the actual like full floors, you know, like we're going in and making sure everything that is being done can be taken out and generalized to whatever domain we want. So the danger zone, that's also very important. So there's 3 different danger zones for traditional research, software, and intuition. So intuition is something that I right now am seeing all the time because I have some insights or I have some domain expertise for geology, and say when I'm working on projects at Southern Methodist, I'm usually the only earth scientist there. Most of the other guys are engineers or physicists, and they're like, well, yeah, we don't really care about that. So there, my intuition kind of takes me down a rabbit hole, which could be a big problem depending on what type of project you're working on. But for here, your intuition is needed for machine learning. So how that ties in with me being able to have my intuition for the groups that I'm in as a geologist, say if we were given an assignment and they had no idea how to build a good predictive model based on what's given to them. Say the professor's like, all right, we're going to do a seismic survey today, and you're all going to build a predicting model for 4,000 feet below the surface in this area. They're all going to be like, oh, crap. Now my intuition is good. But if they utilize their intuition wrong, that's a bad model. So you have to be careful with how you utilize your intuition when building these algorithms. They're very, very, very delicate to what you do. Next. All right, so the outline, we'll be starting off with a brief overview of what data science is, and then we'll go over to the types of machine learning. And next I read the paper, the LHC paper, where they actually were utilizing deep learning and machine learning to help out with neutrino and muon interactions. So I'll just give a quick survey of that. Since this is a physics department, I thought that would be a nice paper. It's relevant, published August 2018. Next, I'll jump into my side of the geology, geophysics. And when we get to that part, I'm actually going to go to my computer and we can look at Jupyter notebooks. And we'll go through code and output, and you can see how it looks in like actual data science workflow. For the physics part, it's more of just I covered the paper, I went through and summarized what they were doing, how it was important to data science, not just physics. Then I will conclude with some issues to keep in mind, because just like any other field, when there's a hype word or there's a huge demand for a new domain that's being brought up, like data science, there's so many bad negative things that come with that. So different companies, I've interviewed like 3 times now, and every time I go there, they're super excited to get data science into their company. They're willing to spend big money because it's coming from like the higher ups. The stakeholders are coming down saying, we need data scientists to give us more insight. How are we going to utilize our data? And then they have no idea what to do. Like, I haven't gotten hired yet, but from what I've heard from people that have, and people that I am in school with are actually directors for big companies, and they hire data scientists. So they're getting this degree so they can understand more what their workers are doing and manage them better. Because right now in data science, there's a lack of data science leadership, since it's fairly new, even though statistics has been around since Dr. Friedman was riding his bicycle.
That's a long time. We didn't have bicycles.
No. Walking the dinosaurs.
Walking the dinosaurs.
All right, so that's another key issue that's going on. And then considerations would be to be more open, to become more interdisciplinary. Like, that is one of my most favorite things. Is I started a master's program in geology, and my thesis project ended up getting canceled due to the landowners in Central Texas. They didn't want nobody on their land came chasing me off with shotguns. And my thesis advisor was this short little lady, and she was like, oh my God, you need to cancel your project. We can't be out there no more. So I was like, all right, see you later. I was driving to Stephen F. Austin, which is a long drive. So keep that in mind. All right, so what is data science? As you can see with the graph on the right, it's mostly comprised of scientists that come from mathematics, statistics, computer science, natural sciences, and engineering. And another interesting part is the business. So this is like the market research, the economists, and the market analysis people that come in. They have really, really good intuition and insights on how to wrangle the right data, and they can apply that with a little bit of training to a different domain. So like they'll come in, say they're building a recommender system for Netflix, and then their boss just knows that they're a rock star. Next thing you know, they're working for like, who knows, like say an oil and gas company or something. Utilizing those same skills, but just tweaking how they're actually doing it. So that's what's really cool about data science. It's almost as pure, not as pure as you mathematicians and physicists, but it's getting there. You guys are definitely helping lead the way with actually giving us the tools that we need. And then social science. Who here has read a paper and like anyone taking like Sociology 101 to get one of those requirements knocked off for your degree plan? And you read papers about all these social experiments that have gone on where they take N amount of people and give them this drug. That's all statistics, right? So those psychologists and social scientists have been utilizing probability, maximum likelihood, and multivariate and univariate, bivariate statistics to produce good results with their research with small sample sizes. What we do in machine learning and deep learning is we take the same approaches, but now instead of maximum likelihood just being maximum likelihood, now that's actually what the deep learning model is trying to like maximize. They want to have the maximum likelihood, which is pretty much how the model works. It's learning, and then it's being taught that it's wrong, and it makes a correction, and it learns again. And it keeps going over and over and over. All those years, we can go back and read papers. You have to take advanced statistics courses, causal inference, and you have to figure out exactly how they're able to apply that to the general population and not just the sample. I already talked about economics. Stocks, there's a lot of people that want to predict stocks. And what I find really interesting is who's ever read like a news article where you see somebody that works at a stock company in New York that's getting blasted or getting fired because they messed up? Like, you don't ever see that, right? That's because if they mess up, they're getting fired. So I find it very interesting, and I would love to work with somebody that actually has done that. Being able to produce good models that predict and make money, that's their life. They must have something going like that. They must have some sort of insight that I would like to tap into. So if you ever come across somebody that's doing the financing, or you get a talk from somebody, get their business card, look them up on LinkedIn, and try to learn from them. Maybe ask them what's their favorite book that they recommend to read. Anything. Because there's something that they're doing. It's crazy competitive. And I can't imagine that type of stress. Like, even just a geologist, if you don't get a job because whatever, and you're at a rig, you can still go and make $100,000 sitting in a trailer, looking at samples, analyzing them, and saying what minerals are in there. Those guys, if they mess up, I don't even know. Like, can't imagine. Now, you can see there, I found a picture of Dr. Friedman and colorized it from like 1976, I think. No, I'm just kidding. All right, so data science as its practice is a blend of Red Bull-fueled hacking and espresso-inspired statistics. That is my favorite quote of what data science is. So the Red Bull-fueled hacking, I'm not going to lie, I stay up really late all the time. I have 5 kids, and I've been married for almost 13 years, so I don't start doing homework until like 8 p.m. So I stay up all night. And then I actually have class this semester. It's Monday and Wednesday from 8:30 to 10. So I have class, and then I have to, after that, finish my group work. Everybody I'm working with, they could be anywhere in the world because they all travel through business professionals. But a lot of them are on the East Coast and the West Coast, so you'll see that later with the trend when I talk about it. Most of the data science hubs are on East Coast, West Coast. We're in the middle America. People here that get this type of degree, they usually go to the coast because you get paid more, and there's a lot more opportunities. But I prefer to stay here and be more creative. So actually those links probably won't work right now. But pushing your personal boundaries and also those statistics with data science, that's super important for the field. To be able to move past your niche is the best way to put it. If you're really good at maths, keep doing them. Learn to apply them to a different type of problem. Learn to help solve cancer or anything. Because machine learning is really cool, and data science especially, because I believe it's truly an extension of your mind. So whatever you can think of, if you can teach a computer to do it, it's probably going to do it. But you have to be careful, like we said earlier, with the trash in, trash out. So if you start feeding it bad data, you have to be able to trust. You have that validity part of the skill set. So as you can see, the 50 best jobs for America in 2019, number 1 for like the past 3 years, 4 years, is data scientist. You can see the median base salary is $108,000. And if you go down below, I had to cut it off just to make space, but there's more analyst jobs. So you physicists can all get jobs right away. Every job application I look at, it says degree in physics, mathematics, statistics, computer science, or related. It doesn't even say data science. It always names off those. IBM predicts that the data scientists will sort of 28%. So that's another thing that's really important about data science is there's a huge demand. You'll see all the hype words and all the buzz going around LinkedIn, but there's not enough of us. Like even now, I'm learning, and there's people graduating, and they're getting jobs, getting paid a lot of money real quick. And people just keep coming in, people going out, and there's a shortfall. start clicking on maybe a couple ads on your Facebook, and you'll start seeing more and more schools. I get like Columbia, Cornell, Rice all the time, obviously SMU, but ads will just start popping up for all these different data science programs, online masters, and they're just more and more and more and more and more and more because they're trying to fill that need. And a lot of people are getting paid a lot of money to do it with good education. So as you can see here, so nationally, the average pay is $117,000 with good actual incentives. So you can see like $3,900 to $26,000. So these are like bonuses. So you build a good algorithm, you predict within like say 95% of somebody watching a movie on Netflix because it's rated up on there by what they've watched before or how long they stared at the screen or read the actual film description, and you start building good models like that, you get bonuses. And it's definitely a rewarding career. I've yet to see that, but I got hopes. So in the Houston area, we are paid just below the average pay for the nation. But that's because, like I was saying earlier, the East Coast and the West Coast is where most of the big dollars are. We got the West Coast, Silicon Valley, and then we have all the financial places on the Northeast. But still, the bonuses, they're not very much different. You can see it's $3,664, $25,294, and cost of living is a lot cheaper over here. So that same type of bonus, they're pretty much equal. It's going to be a lot of extra money here. And I go to talks. There's going to be a talk coming up at Rice March 4th through the 6th. It's for high computing performance, I believe it is, or high computing. It's for like high computing. And every time I go to those little things, you get a huge student discount, first of all, so it's always like 20 or 40 bucks. And you just network like crazy. Get so many business cards and so many people, and then once I tell them I'm in an online master's, you always get like a LinkedIn friend or connection from some vice president of a startup here in Houston. And you're like, whoa, like this guy's the top of his business, and he's over here like, when are you graduating? That type of stuff. So definitely get yourself out there. I haven't done any blogging or anything, but I've been listening to podcasts, and a lot of them say that having a blog or even just answering questions on different sites. So like if you go onto like say a mathematical site and you're answering questions and tutoring people, your name is now on the internet. And in those interwebs, somebody will find you when they search. Say, for example, you're interested in machine learning and you figure out the best way to minimize an R and N, and then your name's now connected to that. When someone searches for it, you're going to pop up. All right, so the typical data scientist for 2019 is predominantly male. It's pretty sad at 69%. And it's about true in my program. There's not very many women. I don't know why. Maybe there's some weird bias in the business domain I'm not aware of. I've never been a businessman. But I find that unfair. So the average workforce is 8 years. That's quite interesting. So that goes to show that there's a lot of people with prior experience that are now using the title data scientist or using their skills that they've been building and transferring them over. Bilingual, that's really cool. Like, I wish I knew more than English. I'm learning computer languages, so I guess technically I'm a little bit, but not really. I have group members right now that are from Russia, and it's like, just let me see your code. I can't barely understand what they're saying, so just let me see your code. Python and R are the top two. Python's definitely a language. If you want to start learning, if you're not doing it now, start learning Python. Go to Udemy or Udacity, Coursera, or even DataCamp and just learn Python. It's open source, free to download. And there's so many tutorials you can go. Start teaching yourself. You can just basic, it's like using math on a computer. You can set variables to whatever you want. You can set up equations and you can solve them just like you would on a piece of paper. As you can see for the industries throughout the different countries, so USA is dominantly technology and IT, the finance, and then healthcare. That's interesting to me because I see so many people utilizing data science. So they must not be data scientists, but they're doing phenomenal things in healthcare. They're like, machines are better at finding tumors than humans are with like radiology and x-rays. So I don't understand why it's so small. As you can see, the competitors, India, all of Europe, and UK, they're pretty much about the same. Well, they all have better healthcare than we do. But. All right, so let's go ahead and start with machine learning, what it is. Machine learning is a system that can recognize patterns. It is using mathematical algorithms to learn insights from data without explicitly programming them to do so. There's 3 main types. You have supervised, unsupervised, and reinforced learning. So as you can see here, scikit-learn is really big for machine learning in Python, and it's definitely really good to start getting the skills now. Plant the seed, you know, just let that seed get in there and give it some water every once in a while. I know school's rough, especially as an undergrad. When you get to graduate school, it's a lot better. You're treated more like a human. So that's good. Keep that in mind. So as you can see, this little roadmap shows you when you're starting with a project, if you have more than 50 samples, you can continue to go down and decipher which type of model am I going to be using. So model, algorithm, they're the same thing. And based on this little workflow, it'll help you understand how to utilize machine learning for its best intended purposes. So go explore scikit-learn.org and learn. I'm glad you asked. So supervised, that'll be the next slide. So what machine learning isn't. So this is a perfect little comic.
SUV,
What was that?
I think I recognize the guy you're talking
Oh yeah, it's perfect. Like a lot of people see machine learning, especially in the geology, they're like, oh, it's a black box. Like everything's black box. Like, I don't know what, they have like some weird bias towards mathematics and statistics or something, but everything's a black box. This is your machine learning system. Yep. So you pour the data into this big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? Just stir the pile until they start looking right. So a little normalization for you there. So what machine learning isn't, it is not a black box. Some people can build it to be a black box, and that's bad. That's where you have to maintain those skill sets, like that Venn diagram helps you stay true and narrow and straight and on the path, you know. So you can't really see it with this projector, but this is a support vector where we have the actual line that goes through and separates the 2 different classes, and then you can see the decision boundaries that are orthogonal. They're weighted matrices, but you can't really tell there. And I can give this PowerPoint to Dr. Friedman. You can distribute it. You guys can download it. I didn't do like a slide share or anything. All right, so supervised learning. Supervised learning is where you are telling the machine the answer and all of the data that it needs to predict that answer, and then you train it. So as you can see in this good diagram here, the machine is going to take everything that's going in, so you can see there's a cat, whatever that is, another little cat. Well, I guess those are all cats. So we're teaching it cats, right? So the machine is doing what it's told. This is what cats look like. Memorize them, learn them, understand all their features. So features and variables, interchangeable word. Next, you go to the next step, and you're going to apply another data set to that where it's going to be tested. So you train it. This is what you should know a cat looks like. And then you test it by throwing in a mixture of animals, and then you're measuring its accuracy by seeing how it does. So it should know exactly what a cat looks like and separate the cats from non-cats. That is the basic way to understand how supervised machine learning is. You have a training set and you have a test set, but within your training set, you know the answers, the machine knows the answers, it's labeled, all of the values are there. So there's classification, supervised learning, and regression. And for unsupervised, there's, I guess we'll go to the next one. So these are some common algorithms for supervised. So for classification, you have the support vector. Machine, it's a it's based off the support vector machine with its classification. So you have to work your code and create binary or Boolean responses. So it learns true or false, boy or girl, cat, dog, or just zeros and ones.
This is more qualitative, and then the regression is like line investigation.
Yes, exactly. And for regression, yep, you start doing the continuous variables, you're predicting numbers, and then you get into the sophisticated statistics with elastic net, lasso, and ridge regression. But most people, when they do supervised, they're either classifying huge amount of data into groups, but it's not like clustering. They're actually classified because the model has been trained on what to look for and what the answer is, right? For unsupervised, it doesn't know the answer. It's straight. You just tell it the math, you tell it how to separate and find and analyze all the different dimensions, and then you throw it all into there and it puts everything into a space. So it takes the matrices. You have to actually get the matrix down into a 2x2 array, so a 2D space, and then the answer will be turned into one dimension, and that's where you can actually take it and project and figure out exactly where it is. So it's kind of fun. So as you can see here, for unsupervised, you don't have to do any labeling of the answer. And this is, what's nice about this is this helps speed up your workflow, because in the real world, most data comes unstructured and just, we call it like crap, you know, like you get something and they're like, fix this or solve this problem. Here's all the data I have, and they just dump it on you, and you're like, well, all right. Most of your time, like 80% they say, is cleaning, labeling, and fixing all the stuff. Or you'll see later with the petrophysical stuff, certain wells will name attribute differently, but it's the same exact thing. So you have to fix the names because the machine's not going to understand, well, why is this one and this one named different, but they're behaving the same. You have to fix that, or your model won't be optimized to its best. So with unsupervised, plug it all in, and it does a dimensionality reduction. So this is where you can see you just went from 6 different to 2, reduced it down into 2 different actual dimensions. And there's clustering and anomaly detection. So clustering, that is like super, super nice to use when you're trying to understand your data and see if there's any underlying structure that you can pull out and understand like a little more about it, instead of just looking at it as an array of garbage. So this helps you understand the array better with clustering. Anomaly detection is mostly used for actually like finding something that's not supposed to be the way it is. So like networks, like I'm learning in my network security course, they'll utilize unsupervised that's continuously running through the network. And if there's a hacker that breaks into the network and starts pulling data from one server and storing it into a different server and nobody knows it, the anomaly detection will go in there and be like, hey, this is not a normal path. It's broken off and there's something over here. And then that's where the data scientist can go in and fix it and be like, oh, we have to start reorganizing and retraining, because every model changes. So even the people that are hacking, they're using the same skills against you, and then you're just going back and forth. How do I outcompete them? So that's kind of fun too. All right, so here's some common algorithms, and there's many more. You can Google it, and it's just like lists and lists and lists. But these are common ones that I've been getting trained on and we're using. So for clustering, you can have the mean shift variational, Bayesian, Gaussian mixture. A lot of it's just like in every other science, there's acronyms. Mini batch k-means, spectral clustering, Gaussian mixture model, and then artificial neural networks. And for dimensionality reduction, I really love PCA, so I highly suggest go and learn like how it works mathematically for you math guys, and for you physicist guys, you guys can go and plot it up and run some experiments, because I think it would be really cool to see how that can be played with. Isomap spectral embedding and locally linear embedding. So reinforcement learning. This is where the subfield of deep learning starts to branch off from machine learning. So for reinforcement learning, it is all based off the Markov decision process, which is where you can see this super famous diagram of how a decision process in reinforcement learning works. You have the agent, who is independent an environment where everything that the agent is learning from comes from. And as an action happens, the agent has to decide what the reward is going to be and what state they're going to take. So the best way to put it is, say if you're playing tic-tac-toe, the agent would see that you put a circle and it would make a choice, like, well, if I put an X over here, what is my reward? That is what the machine does, but obviously they're utilizing a lot of math. So the Markov decision process puts all of its decisions, states, actions, and rewards into a sequence, just a flattened array. And this sequence of information is then built into a probability, a conditional probability. Yep.
How does the reward work? How you reward?
Oh, we decide the rewards. So we'll tell it what functions to use for its steps and actions, and then we tell it its rewards. Like if you make a circle there and it should have been an O, and then they win, you are negative. There's a negative like annotation. Mm-hmm. Yep. So in the back end, the mathematics is trying to find the best maximum likelihood that you're going to make all the right choices. So it's kind of fun. It's like a big guess. And you can, what's nice about reinforcement learning is you can just let it go once you program it, and you can just allow the instances to run 1,000 times over, and when it's done, retrain it again, and it'll just keep learning. And the more data, the better. All right. Oops. All right, so common algorithms. The Q-learning, which utilizes the Q function, which is like from the 50s. And what the Q function does is it builds actual probabilities into a table, and that's how you can kind of visualize the tic-tac-toe, where it's building probabilities of choices. The temporal difference learning, the learning agent learns to predict the expected value. So this is nice because it's trying to predict instead of just react. It's being more progressive. Gradient descent, optimization towards the global minimum. So gradient descent takes a lot of computing power, and that's definitely the best way to go. But what I love about Python is a lot of the gradient descent is already done for you. There's like automatic differentiation going on in the background. So utilizing like PyTorch and TensorFlow, it's already done. So your model runs a lot faster, and you don't have to wait. Like, well, I probably won't have to run them because I don't want to run out of time. But there's times when you run like a grid search with cross-validation, it'll take like 30 minutes. And that's only with like 20,000 different instances with like 5 folds. And like I said earlier, almost all reinforcement learning problems can be formalized with the Markov decision process. So learn the Markov decision process, and you can take any other different method that is brought, because machine learning, data science, there's new stuff coming out every day. You can just take it all back, do some derivatives, do all that math to it, and figure out how does it look in a Markov decision process, and you'll have that full understanding. So here's a little comparison of the algorithms with their speed for prediction training and how much memory and required tuning. That's how you adjust the actual parameters. And then like, what is it generally used for? So you can see like logistic regression and linear support vector machines. They're very fast, train fast, use a small amount of memory, and the tuning is very minimum. You usually just choose a kernel that's linear, and you can choose the cost function and the gamma, which is pretty much telling it how much data to look at and how much to choose from that amount that it's looking at. Decision trees, they're also fast, small memory with some tuning. So with decision trees, I like them, but I'm not a huge fan because they're very prone to overfit. So be careful with that. You'll have like a model that has 99% prediction accuracy, and then you're like, oh, sweet. And then you try it on a new data set that it's never seen before, and you get like 30. You're like, I suck. I just said this was the best model ever, and now you just embarrassed yourself. So be careful with decision trees, and you can trim the leaves and limbs. So that's the way they're built. There's different nodes, and then it'll either stem down into a leaf and a limb. Yep, and you can trim them up And that helps get rid of the bias towards overfitting. But they're very fast too. So that's why a lot of people use them, because it's quick. But be careful. So good generalist, but prone to overfitting. Nonlinear support vector machines and logistic regression. So that's where you can utilize like the principal component analysis. So run a PCA, account for all of the data's variance, say like 95%, cut off all the other variables and features that don't account for. So that last 5%, you can just cut it off. Now you just reduce the dimensionality. Who knows how much? It could be like tenfold, depending on your amount of features. And then from there, you can run a logistic regression with really good actual features that are going to predict 95% and better, hopefully. Depends on the amount of interaction terms you need. So nearest neighbor, we'll go over an example with that today. It is kind of slow at times, depending on how much data it's actually being used. Training speed is minimal. It does use some memory, so your CPU would start overworking, but then your RAM is going to be like clocking out.
Is that really that big of a problem in the industry right now? Because people, like, standard's like 16 gigabytes, right?
Yeah, so like what's recommended is a quad i7 and 16 gigs of RAM. That's like what I use. But there's obviously, I can't even imagine going into like those high-tech firms or research and development. And then virtual computers.
So people still are trying to compress.
Yeah.
Okay.
But what's nice is, like, as a data scientist, you're doing a lot of this stuff. I don't know how much access to the data you have, but you can do a lot of this like on your home computer. And if you're a consultant, I don't know if you're gonna be able to buy like MacBook Pros, or not MacBook Pros, but the iMac Pros. They're like $11,000. You know, I'm sure that could do it really fast, but this computer is only like $2,000, and it does it all fairly quickly. Next we have the naive Bayes. It's all pretty much fast, but it does utilize a little bit of memory. And it's huge in, as you can see, the text and spam filtering. So you gotta love that conditional probability. And ensembles. So what's cool about ensembles is it's actually taking the actual instances and it's randomly deleting some. And there's some cool research out there. Just Google like ensembles and machine learning, and you can just start diving in and let curiosity lead the way. The models are predicting better by randomly deleting some of the nodes in a neural network, which is like weird to me, because that's exactly all these hidden layers that build up a neural network. You have an input, the hidden layers, and then an output. Everything in between, they're just randomly deleting stuff, and it's computing better. So that's fairly interesting. But they're used for high accuracy, good performance for small to medium-sized data sets. So small data sets, that's definitely a problem with a lot of companies. You know, another hype word, big data. So a lot of people want big data, and they spend money on big data. But the cheap data, that's still big data, is the unstructured, unlabeled, so you're stuck with doing like the PCAs. All right. Let's go ahead and move into the overview of the physics stuff. All right, so the LHC in machine learning. There's the title of the paper, Machine Learning at the Energy and Intensity Frontiers of Particle Physics. Has anyone read the paper from August 2018, published in Nature? I had to rent it for $8.99.
Oh my God.
And then I screenshotted every page, because it was only good for 48 hours. All right, so as you can see, the use of machine learning at the LHC has actually helped them identify the Higgs boson. So that's really cool. I didn't know that. I learned that investigating this paper. The paper, what I really liked about it is it describes how the LHC utilizes machine learning and deep learning to further the field, and also...
So this is sort of reading, right?
Mm-hmm. Yep, and so they describe how they use it to simulate data, how they utilize their simulated data in actual models. So like the 1 million receivers, sensors that collect the particles being collided, they're actually able to model their simulated data with that data, and they make a hybrid. We'll talk about that in like a couple slides. But it's really cool because they're just thinking outside the box, and that was what really impressed me, is leave it to the physicist to be like, how can I make this data better? And they came up, they probably branched out and learned computer science and programming and phoned a friend or something, but they made it work. And there's some like bad talk about data science in physics, so be cautious of that, but also be aware. Just like I said earlier with the trash in, trash out, you have to be able to validify the data that you're using, and this paper does an excellent job of showing how they test and train and have actual valid simulated data, and also the data that they're using is good. I highly recommend this paper. If you're looking to physics and also even just mathematics, because it doesn't go too deep, but it gives you all the stuff you need to Google. And the references, they're awesome. Like I stayed up till like 5 in the morning just going through all the different stuff, so I wouldn't recommend that during midterms, but I couldn't help myself. All right, so the paper highlights the boosted decision trees, which they're no longer using, but this paper highlights how they utilize boosted decision trees, neural networks, and then NOVA convolution neural networks, and the micro Boone, which is like the neutrino recurrent neural network. And this picture here on the left shows all of the data that they mapped the Higgs boson with, so that's cool. You can see the errors and all the different decays as it steps down. And BDT, that's boosted decision tree. All right, so for the neutrino feature extraction, the NOVA convolution neural network, the experimenters created a hybrid experiment where they took simulated data, which was, so their simulated data is right here, the very top part, taking pure muon neutrino current or charged current data and replacing the detected muons with simulated electrons. So they know the pure math, and they know the integrity. They know what should happen because they're physicists, and they know that doing this is going to cause something. And their algorithms were able to map it. So they were able to visualize a rare event that they'll probably, who knows when they're going to see it at the LHC, you know. But they were able to visualize it with real data and simulated data. So that thinking outside the box again is so cool. So these hybrid data events allowed NOVA's algorithm to be studied on rare electron neutrino charged current interactions. The NOVA neutrino interaction convolution neural network model is used to extract neutrino features from the charged current interactions projected into a 2D space. So the 2D space is what's key because it allows everything to be flattened and separated. And you can see that it's all distributed with a stochastic neighbor embedding, which gives a little bit of overlap. That's just, if you go and check out the algorithm, you'll see that with the T distribution, it's allowing a little bit of overlap. It's not normal Gaussian where everything's spread out. No. Yeah, this is convolutional. The recurrent comes with the micro Boone, and what's cool about that, I'll go over in like the next slide, I think it is. But with the convolutional neural network, this is them creating all of the strict maths, you know, but using machine learning to do way more than any human could do. Yes?
So, you say this is mainly supervised learning?
This is all supervised. That's their domain expertise is how this is valid. I would be interested to see, well, Dr. Friedman and his expertise in entropy would probably be able to predict something, but we have to be able to control entropy, and when entropy is lost in data science, we start measuring the loss of entropy as information gain. So there's another thing you can Google that's really cool, and that's all from sophisticated statistics, but information gain is a very useful measurement.
So it's inverse to entropy?
When you lose entropy, you're gaining information with feature space. So we try to decrease the entropy. And this NOVA convolution neural network approach is used to ensure that the groupings match the intuition about the physical processes being studied, inspect what you expect for model validity. So they pretty much were able to simulate what they know works with the maths in a model. That's pretty awesome. And I wish the color of the projector did it justice, but you could see in high def. Like, mm-hmm. Yes. They didn't really talk about how many deep layers. So that was all like wave topped. So the microboon RNN. So this is where they took, as you can see in this picture, the yellow square is what they built and predicted with the RNN. So the recurrent neural network, it's continuously learning. So you train it, and then you take that difference, so what was observed and what was predicted, and you get the difference function, take its derivative, and you back propagate through, and you teach the features to adjust, and then you do it again and again and again and again and again and again and again, and it learns to predict very well. So their big problem was the simulated data is used to train the model, and then experimental data observed is overlaid on a cosmic ray background image to match the centimeter scale neutrino interactions. So in the paper they're talking about having a really hard time finding the neutrino interactions because it's so tiny. So what they did was teach this recurrent neural network how it's going to interact, because they know the maths, they know the physics, their intuition led them down the right path. It predicted where it should happen in the yellow box, and then the observed data was in the red box. So that's pretty awesome. It helped zoom in a little bit, helped them find what they're looking for. So the use of the recurrent neural network as an input feature, so they took this RNN was built from a hidden layer, which they don't really describe which attributes it was, because each hidden layer is an attribute. So say if you have 50 attributes and you're building a model to predict one, so 49 of those would be a hidden layer, and everything else in between. So you'd have the input, each layer is an attribute, and then the output would be that last one, a prediction of the last one. So the use of the RNN as an input feature to the boosted decision tree and the CNN at the Atlas experiment reduced the misidentification rate by a factor of 3 relative to the machine learning results without the RNN. So they were able to reduce it by a factor of 3, which is awesome. And here's a good visualization of that reduction. So you can see the red was raw, and then with clustering, machine learning clustering, and then as you can see with that RNN feature added, correcting where it should be, the neutrino interaction was then mapped and found. So it's definitely good research to look into. A lot of the stuff was coming from France, a lot of French physicists. So I don't know if you're following any of their research, but are any of you guys familiar with ResearchGate? Go on ResearchGate, just look up some of the authors and the sightings, and you can follow them. And every time they push a paper, it's going to notify you. And then that's how you just stay current and stay curious. So the use of the RNN, that's pretty redundant. You can see here for machine learning, they've been using it since 2011. And these are the different, so each of these different experiments, these are all different organizations doing experiments, they're increased in data. So they acquired 51%, 85%, 73%, 15%, and then down here, 125%. So machine learning is just increasing the amount of information they're able to keep and capture. Because they also use machine learning to cut all the bad data that has like the signal interference. So like when the sensors record everything, machine learning automatically goes in there and extracts what's good and what's bad, and they cut the data set, compress it from crazy like petabytes down to terabytes, which is still a lot of data. You guys would definitely, if you want to do anything with this, you're going to have to utilize a good subsampling algorithm to randomly select. All right, let's see. Got about 8 minutes. Shouldn't take too long. So for the geology, geophysics part, I wanted to show you guys what it looks like in Jupyter notebook. So for this first one, it's called a facies classification. And what this is I got this code going to a Data Science Institute machine learning workshop through University of Houston. And it was really cool. You guys should look into that school if you're looking for grad schools. Their data science program is up and coming. Like I don't even think it's technically for undergrad, it's not there yet, but they plan on having a undergraduate major, graduate certificates that I think are there now, but actual graduate degrees. They're going to have all that. So for the facies, it's taking data from well logs, as you can see, different formations. So a facies is a specific environment that geologists look for that tells you where it is on like geography. So if you're looking at the beach, if you're looking at offshore, deep offshore, or you're looking at a fluvial interaction with salt water and so like a marsh, or a lagoon, that's what a facies is. It's the rocks tell the story. We go through and we find it, and we utilize qualitative skills and descriptive skills. This is cool because it's utilizing quantitative skills and machine learning to speed up our processes. So this is what the data looks like. It's just classified. So what type of learning is it when it has the answer? Yeah, what is it? Supervised, unsupervised, or reinforced? Supervised. So we're giving it the answer, right? We're telling it it's part of facies 3. So this row right here is, or actually this column for this well right here, this well, all of its information is facies 3. And we go through, and the machine will take all that and account for it. So as a data scientist, we go through and we start figuring out what's unique about each of these. So here you can see the code. Nope, there's no code yet. So you can see like for sandstones, there's an adjacent facies for number 2 because 1 is next to 2 and then so on. 2 is next to 1 and 3. So all of this is going to give us overlap in their data. So here's some code on how you could see we're setting up the training data as an actual feature, and then we're renaming it as a category. So we're telling Python that it's a category feature, like type. It's not just an integer or a float value, it's a category. And then for formation, do the same thing. And then well name is unique, which lets Python understand that it's a unique feature that will be searched for later. For facies colors, so this right here, this code is setting all of the different colors for a specific environment. And then we're also creating labels to go with the colors. And then here's a huge loop that goes through and makes this really pretty plot based off the basic data. So when I was learning geology, I had to do all this by hand, by looking at these, finding the peaks, and then correlating them all the way across. So I would look at the gamma ray peak, go to the next peak, all the way over, and then draw a line here. And then
are these wireline logs?
Mm-hmm. So wireline logs, and I'd figure out what it is. And I'd have to look at the actual rock descriptions and tell you what facies it is. So here we...
Facies mean was it the geological environment or
Yep.
something or other that's just a fancy geological word?
Yeah, it's geology makes up a lot of words. Most of
We
it's
do in physics.
derived from Latin. So there's one well. Here's another well. This is just showing you how they do it, classify the wells. All right, so visualizing the distribution of actual rock types and their colors. So it's understanding. Here you can see a scatter plot matrix that shows all the relationships between each feature. So if I plot feature 1 with feature 2, it has a distribution like this. So this is where we can utilize statistics and understand what type of distribution we're dealing with. Do I need to do anything to that feature to change it to be normal? Like, is it skewed? Do I need to take the log? You got to figure all that out by visualizing your data. So here's just a description of the actual features. But the good part, this is to show you how simple Python is. So from sklearn import pre-processing. Now I'm going to do, I'm going to take x and I'm going to transpose it and go from an n-dimensional array into just a single vector, a 1D vector. And it's just done with 2 lines of code. And then from there, you can train. You set up your variables as train and test. Then you can actually import the support vector machine. We usually rename it as something so we know what we're doing. And we can have reproducibility with our code when someone else comes through and reads it. You're not just like, oh, what does that variable mean? You got to put it all in there. There's lots of descriptions. But from there, you can just fit. You can do model.fit x comma y. So here's the x and there's the y. And it does it. Then you can do prediction. So you name the prediction, and then you do model.predict, whatever your variable is that you're trying to predict inside there, which is the y.
Did you start in your training? How many training samples?
This was about 3,000.
So not a huge number.
No, this is a small one. For when I get to my part, I got to kind of hurry. We got up to like close to 30,000, and it ran.
Not huge.
Yeah, it's not big data. So here you can see a different confusion matrix that's showing you all the actually predictions. So is it good or is it bad? And it shows you what they are. It's not a very good visualization. Now you have to define to be more Pythonic, they call it. So you want to set up your code to be more Pythonic, which is like, this is where computer science comes in. So you're not like no longer just being mathematician, statistician, or a scientist. You got to become a computer scientist and learn how to code and tell the computer to give you something, because it usually gives you a better result than just utilizing the package, where you could have just said accuracy, like model.accuracy. It wouldn't be as perfect. So he showed this here in this code, how you can go through and define everything you want to give you your actual accuracy. So the facies classification accuracy, 63%. And then being able to classify the adjacent ones. So the facies above and below was 91%. So then after that, he's in a hypertune. Well, here he's visualizing the actual accuracy. So visualizations are important. You can see how each model, utilizing a different gamma, was able to be, or how its accuracy acted as the gamma was used. All right, so here they choose the most optimum C cost function and gamma value. So 10 and 1 is what they decided. Now they're going to build a new confusion matrix, visualize it, and then right down here, they're going to start applying the classification and transformation. So they're going to take their unknown, transform it to a scalar, so from vector to scalar, and then their y unknown predict, so they're doing another prediction about the facies, so the unknown part, and then it prints all of the different features, which is across the top, the variables, and the data that goes with it. And then you can see they plot it here. So do you remember that very top square was all orange last time? So now it's been tuned, and you're able to see that the data is telling us that there's more to it going on, and there's some inner fingered sandstones, that type of stuff. So it gives you more insight into your actual, if you're being a geologist and you're trying to figure out exactly, because when you're out in the field and you look at this rock, you're like, oh, there's sandstone, there's siltstone, there's sandstone, oh, there's a shale. A lot of the times the wireline logs don't tell you that. You have to go through and actually like really peek at it. This speeds up the human process. All right, so here's the petrophysical well log application. So I'm a little bit over, so I'm going to kind of go a little bit fast. So this is what it looks like to load all the data. I'm just setting a name, and I'm telling pandas, which is a package within Python, to read the Excel file. So it's coming as Excel. And oil and gas, they still use Excel. They're like super old school, leave everything as an Excel, or they have other fancy ones called LAS files, which are a little bit harder to put into pandas or into Python, but there's packages out there that do it. So here you can see here's all the different petrophysical attributes. So like depth, there's actually, I think there's 1, 2, no, it doesn't matter how many there are. But all these different petrophysical aspects are very, very specific to the type of rock. So each rock has obviously the chemistry, right? So you guys know that the chemistry is going to have a specific weight, specific density. All of those aspects are then tied into this model. So here we can describe, so the dot describe gives you pretty much the 5-number summary. So the basic statistics, what's the mean, the min, the max, standard deviation, and first and third quartiles. So you can visualize every different well, see how they're all acting. So like if I was doing this with more time, I'd be looking at the means and the standard deviations and seeing how they're different for each variable. And then as I was talking about earlier, we get messy data. So for this, we have to rename the neutron porosity, and then we have to divide it by 100 because the scales were different. So the model would predict for the same attribute, say one's 1,000, the other one's 1. So by dividing by 100, it brings them all down to a smaller level. In this one, we're going through and renaming everything to the standard name, so they all have the same name, same feature, and the model knows to use it the same across. And then here's a visualization of depth first, the delta time, which is the time, the wavelength. So we go through and visualize each one, say these are key attributes we want to see. See there's this weird spot right here. See this weird line that just flattens out? That's telling us that the log the machine must have went down, or the hole kind of messed up and blew out. Who knows what happened, because it's like 10,000 feet away from where we are. So this is where this is useful, because geologists with this skill set, there's companies that they're telling us we're charging $10,000 to come do this, and it takes like 30 minutes to program. But you can get 10 grand, go out to Midland and be like, you want me to fix your logs? Boom. But it's very competitive. I'm sure friends hire friends, so. See here again, there's that weird missing data. We can go through and impute it, interpolate. So here's a good visualization of how we take X, we transpose all of the rows into a single column, and this is what the training data looks like for X, and then we're going to predict Y. So we go through, now we're setting it up. There's X, here's the features that we want to use, and there's the feature that we want to target. Same for the next well. Vert B and Vert C are 2 different wells. So there's subsampling techniques that we can use. So we're going to use a 90% train, 10% test. Now we're going to utilize the K nearest neighbors here at instance 20. And with the nearest neighbors, we're just utilizing the packages. We're telling the neighbors 5, so every dot is going to be, the Euclidean distance is going to be the same for 5. So it's going to measure everyone to the 5 nearest neighbors, and it'll make sure that it's within that group. We go through, visualize the prediction versus the actual. We see that it's linear, so that's good. Now we know our model will work really well. And then as you can see here, it's predicted is blue, and then the actual is green. So a little bit lower, not too bad. Do it again for the test set. And then that missing data is still missing. So we trained on missing data, it's going to give us the same missing data. So in order to fix that, you'd have to go back and train without the missing data, and then you'll actually get a prediction that fills it in. And then this is where we get all of the errors for validation. So you compare the means, you compare the errors, and you can see the one that has the best mean and the best error is the model that you choose to go to the next step and do more tuning. Yeah, start tuning more. So choose the best model, go to more tuning. So now we're going to use support vector regression, the linear kernel, and a 1232 cost and 10 gamma. Same process. Go through, set up what's going to be test and train, standardize it into a normalized state so that the machine works better. Do a 90-10 split, go through, and then there's the model fitted, and then you can see its visualization, and you can see how the support vector does a little bit better than the k nearest neighbors. So this is a good example of how you can try one method and then go through and try another method, and it may work better, but you can compare eventually. Right here, as you can see, the error is 7.58. I think it was, so that the nearest neighbor error was 7.58. Now it's 6.02, so better model with less error. And go back to the PowerPoint. We're running out of time. Sorry, I went over it, you guys. And so for the quick issues, I talked about it earlier. So the lack of data scientists, the machine learning hype, and model validity, and then obviously the lack of leadership in the field. And considerations for if you want to like start getting more accustomed to what's going to be the future, which is a lot of this stuff is going to take over a lot of jobs, and you're going to have to either be a practitioner or you're going to have to be the one observing and choosing a different field to study. So start learning programming now. Start stay fresh with your math and statistics skills. Expand your domain expertise. Don't be scared to stay in a bubble. You know, like move out, expand your horizons, get out of your comfort zone, and that's it.
You know, we won't be insulted if you leave. We might, people who have questions, stay and we can ask the speaker questions. But if you want, if anyone wants to leave, you know, I know you guys have things to do. Are there a few questions?
Yeah.
Yep.
Can you get very far just doing neural networks for supervised learning? It seems like that can almost, if you have a lot of data and you have a lot of resources, you're not worried about spending the resources. Can't you just learn that one recipe and then be proficient at that?
So there are people that do that, and they just specialize in one area. And there's also a funny term for a well-rounded data scientist that can do it all, like the software, engineering, the computer science, the math, statistics. They call them unicorns. So that's a funny term. So if you want to become a unicorn, you know it all. And if you want to be a specialist, that's where you could do like what you're saying. But yes, there's people that commit to neural networks, and they just dive deep into it.
So can I interrupt? So what you were doing with geology, that was not neural networks. We were using vector. So if you have small data sets, so in geology, you're not going to have huge data sets. That's
No.
sort of the problem. So neural network maybe is not appropriate there. Is that right?
Yeah, because you need lots of data to
You
train.
need for the neural network to work well, you need a lot of data. Is that true? Or
Yes.
So in your geological application.
No, but I've been thinking that if you use text classification, neural or natural language processing to build more data, like say if I create an algorithm that went through GSA's publication database and learned everything and set all those texts and words and maybe predict new research that could be done, or
Plus, if you had access to Exxon's
Yeah.
logs or something.
Oh, yeah.
or,
They probably-
or the oil
That's the
companies,
problem.
That's the problem. So another question. Yeah, it's interesting. So you're dealing with relatively small data sets, so that's an issue.
yeah,
But
there's
you're thinking you could get big data sets in geology. It's just a problem.
nobody wants to give them to you.
You didn't mention military at all. Use of it. I'm quite sure they're real interested in that. So.
Oh yeah, they are. There's a lot of cybersecurity applications, but also the military and statistics have gone back for a really long
They're
time.
setting up a whole force just for this.
hmm
just for cybersecurity.
Oh, yeah,
Might be, you know, lots of jobs. too.
definitely.
Does anybody for big data use anything besides neural networks? Is that pretty much dominates big data?
So they'll make specific neural networks that,
Right.
like I showed with the recurrent neural
Right.
network,
Uh-huh.
where they extract certain features
Right.
to make their neural networks better. But that's all they're doing.
Have you heard of AutoML?
Hmm.
So they're automating, they just search it.
Yeah,
And apparently they even work better than some experts have.
yeah.
So that in the future, you
That's
don't even
that's what
have
I'm
to
saying. The math and statistics. That's what that auto differentiation that's going on. If you
Okay.
forgot to do it or you didn't optimize it good enough,
Right.
your model's not going to be as optimal as theirs.
Right. And then the last question. I'm on the faculty of physics. Can you recommend a way that I could kind of get my feet wet? Can I do it part-time, somehow dabble in consulting companies? Or is there ways to do that in Houston?
I haven't heard of any exactly, but
Okay.
every time I say just go to a conference and just
Okay.
start networking.
Okay.
I'm telling you, everyone that I meet that's a data scientist is
Yeah.
usually a physicist.
Okay.
That's why I was like, this would be perfect. 'Cause
Okay.
let these physics guys, as their undergrads, start realizing it.
But if I didn't want to do it full-time,
Oh, you could do anything on the side you want.
okay. Okay, so just, there's no, is there like a job board where people like just kind of say, I want this one little project done?
Maybe. I haven't seen that.
Okay.
Most of the stuff I see is on LinkedIn.
Okay. Okay.
But yeah, oh
Good
yeah.
talk.
Thank you.
So you were originally geology here,
Hmm.
and I don't know if you did military immediately after that or before.
No, before.
Yeah, no,
Before?
I joined in 2004.
Okay,
Did 8 years, or
Mhm.
almost 9.
okay. But how much knowledge did you have going into this program as far as
Zero
like,
computer knowledge.
Really? Okay.
But
Like,
you had the statistics
Yeah.
knowledge because Dr.
Because
Cecil
the
Howell-
geology, I imagine you had plenty of statistics.
yeah.
I was in petroleum engineering originally at A&M, and so I went through some of the beginner courses. We were talking about shale and everything
Hmm.
several years ago. But I'm helping Dr. Friedman with, we're doing some
Oh, thank you.
Yeah, sorry I had to run out there.
That's fine.
neural network stuff, but I wasn't sure. Like, this skill set's something I'd like to develop,
Yeah,
but I've
start.
kind of already done all my applications at schools.
You can still do it on the side. Look at like DataCamp, Coursera. So Stanford University, the people that actually grade you and give you a certificate, the person that teaches it is like one of the godfathers, they say, like modern godfathers